So if I need less current to the load, can I automatically say, hey, this has to happen since it's in series with the load? Increase line. If line goes up, doesn't I total increase?
Yes.
And just imagine, hey, more current here, but look, as this leg is feeling an increase in current, guess what the Zener's doing at the same time? It's saying, base potential, no. You stay relatively constant, because that's how the Zener works. So if I need less current to the load, VCE, the transistor voltage, has to do what?
Increase.
The VCE from here to here, as the increase in load, or the circuit's being applied, effectively this voltage drop of these series dropping resistors is constant. And if you don't believe me, after I review, I can take you over to the lab and show you. That's why I do this. Everything still has to Kirchhoff out, doesn't it?
Yes, sir.
So we're saying, if I'm increasing, do you think VCE is probably going to go up? Look.
Yes.
Look at that side. Look. If I'm saying this, which is true, it's so small, you think VCE is probably going to do that?
Yes.
It is. And if you don't believe me, you guys done the lab. If you paid attention, you should have seen these things. And if you hadn't, you should have been asking questions. You've already done the labs for all of these regulators. Your retention needs to be a little bit better if you're still like, come on now. Now the load voltage. What's the load voltage supposed to do? Remain relatively constant. Now here's the thing. Reality is going to say what about the load voltage?
Increase a little.
There's going to be a very, 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 very small increase. Those that remember when you did the lab, was this true?
Yes, sir.
That's reality. So we can do like a very small, but it's insignificant to where we can still say, hey, the output voltage is relatively constant. And also at the same time, Q1 is going to conduct a little less anyway to help settle it down. That's the theory behind how this thing works. Now, if you're not down with theory, what do? Know the arrow analysis. Because remember, this is supposed to be just a review. So there's that. The opposite effect is for a decrease. The arrows do what? The opposite. Now, hey, I'm taking that potential and I'm decreasing or putting back to what it was. Well, the opposite effect. Now, just take these, leave that one alone, take this, flip it over, take the load voltage. There's going to be a very, very reality small decrease, but it's still, what's the magic word here? What's the magic word for these regulators? Where is it? Here it is. Nearly. Because we know it's not perfect, but it's such a small change that you can call it pretty much, hey, it's good to go, it's constant. I still have enough potential to drive the circuit I've got plugged into it. Good?
Yes, sir.
These things finally coming to fruition for some of you. Okay. I do the opposite here.
Yes.
Yeah, okay. It's the opposite effect. Increased conduction. Hey, now the line is decreasing. Well, I don't want less current to the load to make that voltage drop go down. I need a little more, so I need Q1 to conduct more. And naturally, load line characteristics, the VCE will decrease. And don't forget, whenever we change the line, what are we affecting? The line voltage. What's actually being affected? The slope of the line, isn't it? It is. Because if I increase the line, aren't I going to get a new cutoff voltage?
Yes.
Because that whatever that increase to is my new cutoff voltage. I'm also going to have a new saturation current, aren't I?
Yes, sir.
So that will affect the slope of the line. But Q point is still going to remain relatively in the center of load line because it's still biased for the active region. Yes?
One of the areas, the applied voltage goes up, the current of Q1 goes down.
Mm-hmm.
But if the line goes up, which is the same as the applied voltage,
Mm-hmm.
then the tested current goes up because of the direct effect.
Mm-hmm.
Then current total is equal to IQ1. So how is one going up and one going down?
Total current and transistor current aren't the same thing.
Well, the one equation says that the total current is equal
Oh,
to IRS
well,
equal to
okay.
IQ1.
Here's what we got. This is what I mean by this. This here. Good catch. Here's what I mean. This is what I mean. We'll call it branch 2. Yeah, I got what you're saying. I got exactly what you're saying. Anyone else see that? I didn't want to say nothing. Damn, Coin, you're good. Yeah. What he's saying is, well, yeah, that wouldn't be right. But if I called this leg branch 2, would that make more sense?
Yes.
Yeah, it would. Because that branch plus this branch equals I total, doesn't it? Yeah, good job. See, you say you don't know what's going on. Come on.
So it's slow at.
All right. Hey, slow is better than nothing. So yes, very good. The load. The aero analysis for the load side is the same, isn't it?
Yes, sir.
They're direct. It's the same thing. It's the same thing. So again, if I take the load, I unplug it, plug a bigger one in. Bigger load times the current that existed there at the time that I'm removing, you know what I'm saying? The load, if I put a bigger one in, it could cause the output voltage to increase, right? So it's the same effect as if the line were to increase, the same deal. So I need a transistor to do what? Conduct less. BCE, increase, load line. Smaller load, here's some current. I'm going to unplug it. Instantaneous, this stuff happens, right?
Yes, I
This is instantaneous compensation that takes place. Here's branch current. Here's a resistor or a load. I'm taking it out and putting a smaller one in. If I put, right, like instantaneously, a smaller load times that current that still like hasn't had a chance to hightail it yet, small current or same current times small load could have a potential to decrease that output voltage. Everybody understand what I'm saying?
Yes,
Yes,
sir.
sir.
Okay. So naturally, the transistor's got to conduct more. VCE will decrease because of the load line characteristics, and they're always going to be inverse. That's all I got to say about that series. How's that horse?